You are welcome to this episode. This is Solomon at Solo for Math. Today we are going to discuss about differentiation of these trigonometric ratios from first principles. It's a continuation of a lesson we had about first principles. So today we want to look at these trigonometric ratios: sine, cos, and tan. Alright, if you're given a function fx equals to sine x. Let's start with sine x. We need to remember this formula here. Last time we said if we want a first derivative of a function from first principles, then it is equal to the limit as small change in x tends to 0 of this function minus the original function, then over the small change in x. So if we have fx as sine x, what is our fx plus the x? This one we know it is equal to, we said where there is x you put x plus the x, so meaning that is our fx plus the x. So we substitute in our formula, which is equal to a limit as small change in x tends to 0 of fx plus the x, which is sine x plus the x, minus fx, which is sine x, over the small change in x. Alright, so we said we take limits, we take a limit after simplifying. So when we continue to simplify, before we take the limits, first expand this. When you expand it, remember your trigonometry there. If you have this is the same as sine x cos the x. Since there is a plus, then here we also have a plus cos x sine the x, then minus this sine x here over the small change in x. Alright, now we are going to take these assumptions here. For small angles, sine of a small angle will always be approximated to that very angle. Then the sine of, the cos of the small angle will always be approximated to 1. So taking that, we can rewrite this as a limit as small change in x tends to 0 of, this one is a 1, so we remain with sine x here, then plus cos x times sine x, sine dx, we said it is approximated to dx, that very small angle, then there is a cos x here, then minus this over a small change in x. So this and this go, so you see we remain with a limit as dx tends to 0 of over small change in x cos x. So these also can go, so remain with the limit as small change tends to 0 of cos x. But since we don't have the small change now in this function, then this one will be just that function, it is cos x, and that is the answer. So it means the derivative of sine x is equal to cos x. Let's look at another example. If our function is cos x, then of course we find a function of x plus small change in x, which is equal to cos x plus small change in x. Okay, so we substitute in our formula. The derivative will be equal to a limit as small change in x tends to 0 of fx plus dx, which is cos x plus dx, minus the function of x, which is cos x, over the small change in x. Alright, so we expand this before we take the limit. So limit as small change in x tends to 0, or when we expand, this will be cos x cos dx. Now you know when we are expanding cos, then if this is a plus, we change it to, here we'll have a minus, so this will be minus sine x sine dx, then this minus cos x all over the small change in x. Yes, we take the same assumptions here, that the sine of a small angle will be approximated to that small angle, then the cos of a small angle will be approximated to 1. So this one gives us a limit as the x tends to 0. This one is 1, so remain with cos x times 1, which is cos x. Then here this will be minus, this is sine dx. We said it is approximated to the small angle, which is dx. Sine x, this sine x is this here, then minus this cos x over dx. So this goes with that, giving us a limit as small change in x tends to 0 of, we remained with a negative dx over dx sine x. So if this and this go, we remain with a limit as the x tends to 0 of a negative sine x. So we can even write this as a negative limit dx tending to 0 of sine x. So since we don't have the x in this function, then this one will be equal to, there's a negative here, negative, then it will remain this function here, sine x. So meaning when you differentiate cos x, you end up with negative sine x. Alright, we are good to go. Finally, let's look at a function of x equaling to tan x. So meaning our f of x plus dx is equal to tan x plus dx. So we are substituting the same formula here. So our derivative, we said, is a limit as the x tends to 0 of this, which is tan x plus dx, minus f of x, which is tan x over dx. Now what we are going to do here, we are going to change this tan into sine and cos, because we already know what sine small x, small change in x, is equal to, and what cos small change in x is equal to when we consider small angles. So we need to convert this tan in terms of cos and sine. So this will be a limit as small change in x tends to 0. We know tan is equal to sine over cos, so meaning this will be sine x plus dx over cos. Allow me just take out this. When I take out 1 over dx, this, it's like 1 over this, it is out. So in brackets, I'm just converting this to sine and cos. So this will be x plus the x, then minus, you do the same here, this is sine x over cos x. Okay, so when we continue to simplify, we shall have a limit as small change in x tends to 0 of 1 over the small change in x into, when we simplify or make this as one fraction, the LCM will be cos x plus small change in x times cos x. So when we divide by this, we get cos x times this, we end up with sine x plus dx cos x minus this minus here. When we divide this by this, we get this times this, it gives us cos x plus dx times sine x. Alright, so here we want to borrow some trigonometrical identities. You remember, if you have where you have like sine a minus b, you'll expand this as sine a cos b minus cos a sine b. So we want to compare this with this. Like this is like our sine, this is like our angle A, which is also here on cos. Then this x is our B, which is also here on the sine. So we want to take, it's like we are having this. Now I want to go to the reverse so that we have it in this form that is simplified. Okay, so it means when we continue with our expansion from this, we have a limit as small change in x tends to 0 of 1 over small change in x into, so this one, since this is our a and this is our b, so it means in the numerator we shall remain with sine a, which is x plus dx, minus b, which is x, over cos x plus dx cos x. Alright, so on simplifying, we can say that this goes with that. So we remain with a limit as small change in x tends to 0 of 1 over dx into sine dx over cos x plus dx into cos x. So considering this assumption, we know that sine of small angle of a small angle is equal to that is approximately that small angle. So meaning this one is simplified to the limit as the x tends to 0 of 1 over this, then this one is approximately equal to a small angle over cos x plus dx cos x. So this will go with that. And now if we take the limits, then we remain with 1 over cos, like where there is this small change in x, we put a 0. Now we are taking the limits, then times cos x When we simplify, this will be 1 over cos x into cos x, which is equal to 1 over cos squared x, which we know as sec squared x. Yes, thank you for watching. Don't forget to subscribe, to share, and to like, and to comment on this video. If you have any questions about this, put them in the comment section. More questions, more examples will be done in the subsequent videos. See you.